Good afternoon or good morning, depending on where you are. My name is Professor Duke Orata. We are going to look at thermal analysis today. Now, when we take two components, that is, when you take two components and heat them together, for example, A and B, we mix different amounts of them and we heat it until we get a homogeneous solution. Homogeneous solution, that means the state of matter is uniform throughout. The solution looks homogeneous, it's not heterogeneous. It looks homogeneous. And then you monitor how its profile changes over time. You monitor the temperature of that system over time. I repeat, you have taken two components, A and B, you have heated them up. You have heated them up to form a homogeneous solution. And then you now monitor the change in temperature with time. And that was the plot which you obtain, the graphical representation which you obtain, plotting the temperature change versus time. The temperature change versus time gives you what are called cooling curves. So you have a mixture of A and B, mixture of A plus B. You heat them up, you apply heat, you heat them up, and you get a homogeneous mixture. And then you cool it and record temperature versus time. Now, what you get here when you plot this graph here is called a cooling curve. Called a cooling curve. Now, let's take an example. What do we get? Now, if we look at a simple eutectic diagram, we have discussed simple eutectic diagrams in one of the lectures. You can go through it. If you take a simple eutectic diagram, having components A and B, A and B, this is XB, more fraction XB, XA, more fraction increasing that direction, 100% A, 100% B. And you take a simple eutectic diagram where you have liquid, that's liquid L. In this compartment, as you see in our discussions on simple eutectic diagrams, we now know this particular point. You'll have A plus liquid, here you'll have B plus liquid, and here you have A plus B. Now, if you take a state point, let's call that state point A. Let's call that state point, let's call it C, because you have used A there. Now, we have a homogeneous mixture. We have a homogeneous mixture, a state point C. It's liquid, homogeneous, state of matter which is uniform throughout. Now, if you cool down this liquid, in the temperature profile where you have temperature versus time, temperature versus time, as you cool this system down, of course the temperature will drop, but it will drop gradually. So from C, you cool it down, it will drop gradually. The temperature drops. Try another pen. The pen looks like this one is fading. They're saying the temperature drops. Let us do it well. It's even worse, so I think we'll still go back to our old one. Slightly better. Slightly better. So, we will have the temperature drop. That means it is changing gradually. So when we reach this point, let's call it C prime, that state point, let's call it C prime, we will have the first crystals of A appearing. First crystals of A appearing. Let's say this particular point, we have the composition of the liquid on the liquid curve. Remember, this is the liquid curve. as, let's call that D. This is C double prime. At C double prime, we have this liquid having composition D. Let's say that is having composition F. And we know that the relative amounts of these components A and L is given by Lever's rule. So this segment here will give you the number of moles of A. This segment here will give you the number of moles of the liquid. And so at that particular point, you have crystallization at point C prime. And so this latent heat of fusion, heat is being released. If heat is being released, then as you are cooling your system and this latent heat being released, that means that the temperature drop will be significantly slowed down, because there is heat being released. As you are lowering the temperature, but there's also heat being released, so that the drop in temperature is now slightly smaller. Slightly smaller. So if you look at that slope, it's less steep. So we are at the point C prime. So here we have latent heat of fusion. And that slows down the cooling process. And so you continue cooling, of course, crystallizing more and more of A. When we reach this particular point, let's call that C triple prime. C triple prime. C triple prime. At this particular point, we now have the three phases coexisting in equilibrium. B, A, and the eutectic mixture. Let's call it U. That's the eutectic mixture. So they're coexisting in equilibrium together with, let's call this GH. But these are A, and that's B, and that is A. So the three phases are coexisting together. We have the eutectic mixture, we have B and A, and based on phase rule, like we have already said in the lectures on simple eutectic diagrams, there are three phases coexisting in equilibrium. So since pressure is constant, phase rule is C minus P plus 1, not 2, because pressure is constant. So we have the two component, we have three phases in equilibrium plus 1, so that is basically 0. So the temperature remains constant at that particular point, C double prime. At C double prime, the temperature remains constant. And that is referred to as the eutectic halt. It's referred to as the eutectic halt. This point here is referred to as the eutectic halt. And remember that point, the variance is 0, or the number of degrees of freedom is 0. It's referred to as the eutectic halt. And then from that point on, now you start losing again heat, and you are just having the solids. Let's call that particular point. Now you're just having solids A and B being cooled. Solids A and B being cooled. Now, it's very important to note that the length of this eutectic halt, the length of the eutectic halt, remember, this is just an axis for time. It will take longer. The temperature remains constant for a long period of time. That's what we call halt. That's like when something is moving and then comes to a halt, stops. So in the same way, temperature was changing, then it comes to a halt. And that's because of the three phases coexisting in equilibrium. So F is 0, so the temperature is constant. So the length of this eutectic halt depends on how close your mixture was, the composition of your mixture was to that of the eutectic mixture. Remember, that is eutectic mixture. That's the eutectic mixture. So if whatever you had mixed and heated so that it formed a homogeneous solution and you are cooling is closer to the eutectic mixture, if they are closer, the eutectic mixture, then this eutectic halt will be longer. If they are far away from the eutectic mixture, then the eutectic halt, the length will be shorter. In other words, the time of constancy of temperature will be smaller. So the length of the eutectic halt depends on how close the composition is to that of the eutectic mixture. mixture. XEU. Very important for us to note. So if you have the eutectic halt will be longer. So if you choose the composition of eutectic mixture, it will be much longer. If it is closer, it will be longer. If it is further from that, it will be very short. So if you plot the times of the eutectic halt, then given that, the maxima will tell you which is the composition of the eutectic mixture. So let's stop at that point. We'll continue with our lectures next time.